Welcome, folks, and thank you for joining us for ARB's research seminar on our completed project entitled Evaluation of Pollutant Emissions from Portable Air Cleaners. My name's Michael Gabor, and I am the contract manager for this project. And before we dive into the main portion of the seminar, I'd like to give a couple introductory remarks. ARB adopted a regulation in 2007 that requires all portable indoor air cleaning devices sold in California to be certified by ARB. To be certified, air cleaners must be tested for electrical safety and ozone emissions, and to meet an ozone emission concentration limit of 0.05 parts per million. Since then, newer and more diverse air cleaning technologies have been marketed, including photocatalytic oxidation, plasma generation, and microbial thermal inactivation. ARB funded this project because there is concern that these newer technologies may generate primary and secondary byproduct emissions that may degrade indoor air quality and may adversely impact health. There has been limited prior research on air cleaners using newer technologies to examine their potential emissions and the effectiveness of the technologies in cleaning the air. Also, the question has been raised whether the air cleaner regulation needs to be expanded to include other pollutant emissions besides ozone. ARB plans to use the results of this project, first of all, to provide guidance to consumers and manufacturers regarding the effectiveness of different technologies, and secondly, we will consider whether the results warrant possible amendments to the air cleaner regulation. We invite you to learn more about ARB's Dynamic Indoor Air Quality Program by visiting our homepage, and the link, of course, is provided on the slide. There you'll find, among other things, a list of ARB-certified air cleaning devices. And now I'd like to introduce today's main seminar speaker, the PI of this project, Dr. Hugo Distalietz. He's a staff scientist and deputy leader of the Indoor Environment Group at the Lawrence Berkeley National Laboratory. He has over 16 years of combined research experience focused on, first of all, understanding the mechanics of indoor pollutants, secondly, reducing exposures to harmful chemicals, and thirdly, developing technologies to advance healthy and energy-efficient built environments. He also published over 50 articles in peer-reviewed journals. And now please join me in welcoming the PI, and I invite him to continue today's seminar on an excellent project that he completed for ARB. Thank you. Oh, excuse me.
Well, thank you, Michael, very much for the introduction, and thanks everyone for being here and for the invitation to present our work. Well, Michael said already a lot about this project, so we are completing today, or this year, this project, and what I will be presenting here is mostly an overview of the main findings. I want to start by thanking the ARB management team, which really has been great in supporting us and the work over this period, and also my colleagues at LBL who participated in the project. A couple of statements there. All what I'm going to be presenting today is our opinions, not necessarily those of the ARB, and also we will not be endorsing any product. That's not the goal of this study. In fact, we won't mention by name any of them. So why do we want to study portable air cleaners? There are a number of good reasons. We think this is a growing market, so these are devices that people are buying and using. So it's important to know how they work, whether there is a potential risk associated with using them, and also in general, what is their efficiency? Do they produce the positive impacts that are perceived, or at least that people think are associated with them. And in fact, what we find is that there are, on one side, there are marketing claims that are sometimes sound really too good to be true, or perhaps exaggerated. At the same time, there are very little regulations or standards that can help us measure that performance well. The main concern is definitely what we call poorly engineered devices. These would be devices that are, for different reasons, become source of pollutants, and that in this study in particular, we focus on 4 groups of pollutants, which are ozone, volatile organic chemicals, VOCs, particulate matter, and reactive oxygen species, or ROS. And finally, we do have some experience in our group with some of these technologies, and we did find, at least in some cases, formaldehyde emissions. So we know that there are some potential issues that are present, and we need to learn more about that. So for the study, the goals were, in the first place, to quantify both primary and secondary emissions. By primary emissions, we define everything that is directly emitted by the air cleaner, and secondary is anything that is formed in the air as a consequence of operating the air cleaner. Removal efficiencies is also an important goal of the study. We want to see how these devices work. And because this is there is such a broad range of technologies, as shown in the slide here, we had to really narrow down the study and look at a few technologies that Michael mentioned before, that are those for which we know the least. And those are the 3 on the right of your slide, what we call newer technologies. These are not necessarily new. Some of these has been around for quite a while, but compared with the ones in the left, which are really very mature technologies, such as filtration, adsorption, these are things that have been studied much more thoroughly. So we think that the newer, the ones on the right, are the ones that require a lot more attention. And these are photocatalysis, non-thermal plasma, and microbial thermal inactivation. So the project had a number of technical tasks. The first one was selecting the air cleaners, and there were a number of criteria for doing that. One is, well, the selection of the technologies that I mentioned before, but also we wanted to focus only on room size devices. So the smaller type of devices that would be used, for example, in a room, or in a bedroom or a living room, but not the more larger industrial type air cleaners that are out there. And the other criterion is that it has to be something that people could buy directly online from, say, retailers or directly manufacturers. So the second task was to develop a laboratory method to carry out the tests, which included some of the methods that we already have in place in the lab to quantify number of pollutants such as VOCs or ozone, and also new methods that had to be developed especially for this project in the case of the ROS. Then we pursued to carry out the tests. We had a sequence of tests performed on each of the 6 devices, and with the outcome of those tests, in the end of the study, we performed the evaluation of the performance by determining emission rates, removal efficiencies, and with a very simple model, we predicted the impact on exposure. So let's go step by step, first of all, looking at what air cleaners did we choose. Photocatalysis is one of the areas that we focus on, and 3 out of the 6 air cleaners were photocatalytic oxidation, or PCO, as they are called in the industry. These are devices that have 2 basic elements. One is a catalyst-coated medium, and the catalyst usually is titanium dioxide. Could be others, but in general, it's titanium dioxide. And the second element is one or several UV lamps that irradiate the catalyst. The catalyst does not do anything unless it is irradiated by UV light. The example in the right of the slide shows just one possible substrate that is used. In this case, it's a honeycomb monolith, but there are many other ways in which the catalyst can be supported. And the principle of operation is very simple. The catalyst is activated by UV light. There are some very reactive species that go to the surface of the catalyst. When the VOCs adsorb on the same surface, they get oxidized and therefore eliminated from the air. It's simple to say there are a number of issues that are listed on the right in red. Some issues have to do with designing and dimensioning. We want to make sure that the photons do reach all the catalysts that we have there. We want to have also enough catalyst for reaction to be significant. Also, we want to have enough capacity in the system to carry out the oxidation through the multi-step process until we really convert the VOCs into inert species such as CO2 and water. Another issue has to do with the choice of the lamps. There are various different UV lamps available. The one on top here is what is called vacuum UV lamp. This is just a mercury vapor enclosed in a quartz container. The radiation that comes out is both 185 and 254 nanometers. And 185 nanometers is a radiation that can photolyze the oxygen molecule in the air and therefore produce ozone. So this lamp does produce ozone. The other two lamps shown here do not produce ozone for different reasons. One, what is called the ozone-free UVC lamp has a coating on the quartz shielding that filters out the 185 radiation and therefore does not dissociate the oxygen molecule in the air. And the UVA lamp, or black light, is one that we are usually much more familiar with, has a different type of coating that converts all that other higher energy radiation into this broad band that is shown in the spectrum on the right. So depending on which lamp is used, then there are consequences for air quality. So here is a summary of the three PCO air cleaners that were used in this study. We call them air cleaner number 1, 2, and 3. And in each case, we have one of the three different lamps that I showed before. In air cleaner number 2, you can see that in addition to the basic configuration of a PCO, you also have a HEPA filter up front, and then there is what they call oxygenated catalyst after the PCO. The oxygenated catalyst probably serving as a catalyst that removes any ozone that may be formed during the process. We also mention here, or show in the slide, the description provided by manufacturers, which give you an idea of how these products are marketed. And you see there is a long list of target pollutants that includes, in general, different types of microbial species, particulate matter in some cases. In all three cases here, we made sure that the VOCs, the volatile organic compounds, were listed as target pollutants. And finally, the price range is also relevant because we were comparing stuff that people would be choosing from the same category. Okay, another technology we were interested in is plasma. Plasma is relatively newer. There aren't that many plasma air cleaners yet in the market, but there are some. In the plasma, we have a very hot air composed of electrons only, but the neutrals and the ions are at room temperature. So what I'm saying is that the kinetic energy of the electrons is much higher than that of the other species, and that's generated by a corona discharge or some other electrical field that is applied to the air. And this is a technology that is not new, has been used for a number of applications, and it's finding more and more applications in air quality. That's why it becomes interesting to look at it in more detail. So these are the other three air cleaners that we are studying. Air cleaner number 4 is our plasma air cleaner, and the other two, number 5 and 6, are microbial inactivation devices that in both cases operate by heating the air. In one case, air cleaner number 5 is a room heater also, and in air cleaner number 6, it only heats the air briefly inside the device, but it doesn't heat the room air. It only heats locally, and that's enough to inactivate microbia. So, and in this case, as you can see, the manufacturer's description does not include VOCs. So these are not necessarily devices that you would use to remove VOCs. Price range, still the same. So once we selected and purchased all the air cleaners, we went on to the next step, which was the development of a method. We used for that purpose our room-sized chamber at LVL. We have a 20-meter cube stainless steel chamber in which we can introduce clean air at different rates. We can adjust the air exchange rate, which in this case was in the range of 0.3 to 0.5 reciprocal hours. We can inject a mixture of VOCs as a target pollutant mixture, and we can keep the concentration of those VOCs constant over many hours. And in this experiment in particular, we introduced each air cleaner inside the chamber and operated it as you would in a regular room. The chamber looks a lot like a small room, so it all is made under conditions that really mimic very well what you would do in a home. We have a number of ports on the chamber also that allows us to collect samples of the different types that I will describe in the next slide. We followed two of the pollutants in a continuous mode. We had instruments that could trace how the concentration of each of those went over time for ozone and ultrafine particles, respectively. And also the other pollutants were collected as an integrated sample. That means we take a sample over a period of typically 1 hour and then analyze offline. The VOCs and carbonyls were performed through methods that are very well known and that we have had in the lab for quite some time, relying on a chromatographic analysis. And for ROS, we developed a new method that is relying on the use of fluorescent probes and a fluorimetric quantification. Let me tell you a little bit more about this because it's newer. We used three. In fact, it's not just one method. We developed 3 methods that look the same. In all cases, we collect air through a medium that then is used as a buffer, so it's used as a reaction medium. We add, in each case, one of these 3 reactants, and this reactant is not fluorescent, but after reacting with this ROS, it becomes fluorescent, and we can measure it by spectrophotometry. And the difference between the 3 probes is precisely the fact that the first one, the one in the left, the CFH, reacts with all ROS that is present. The second one reacts only with peroxides, and the third one reacts only with hydroxyl radicals. So one can have more of an idea of how much of each different species are out there. So each air cleaner was then tested under 2 different conditions. This is one of them, what we call phase 1. Phase 1 is just the empty chamber. We don't introduce any pollutant, so it's just clean air, and we run the air cleaner under clean air. Of course, there is some background level, even if we introduce the air that goes into the chamber goes through an air cleaning system. We still have a couple of PVs background levels of some VOCs, and also a background level of particles. We don't filter out all the particles. Now, after turning on the air cleaner, what we did was follow the concentration of pollutants for typically another 24 hours and collect the sample at the end of that period. Phase 2 looks very similar. The only difference is that before turning on the air cleaner, we introduce our mixture of target pollutants, and we allow that mixture to reach a steady state, collected the sample there at the end of that period, then turn on the air cleaner and allow the air cleaner to operate for another 24 hours, reaching another steady state, and then we collected another sample at that time. This is a list of VOCs that was injected, and the choice of the VOCs was done by looking at the literature, what people find in homes, and here in California in particular, and we try to reproduce as much as possible with these compounds what is found indoors, not just which compounds are found, but also the concentrations. And the total concentration is quite realistic, in the order of 150 to 200 parts per billion. So let me show you some of the results. Let's start with the VOC results, and this is just for one air cleaner number 1, if you remember, it's a photocatalytic air cleaner. We have 2 plots. The plot that is on top is for phase 1. That is what happens in the empty chamber with just background air. The plot in the bottom is for phase 2, and you can see that the y-axis has a very different range of concentrations. In this case, we are introducing our challenge mixture. And in both cases, we see an overall reduction in the concentrations of most VOCs. So when you add them all up, you can see that this air cleaner does have a net effect consisting on reducing the concentrations by a small margin, but still reducing. I'm including in the list in the x-axis, I'm including all the compounds that we are injecting in the chamber and 2 more that you see in the red box on the right. And those 2 are compounds that are typically formed in the PCO process as partially oxidized byproducts. So it was interesting to see that, at least for this air cleaner, we didn't see too much of those compounds being formed. The one compound that did increase its concentration by a small margin is formaldehyde. And that is a commonly found phenomenon in PCO. PCO is well known for producing some formaldehyde as a partially oxidized byproduct of many other VOCs. Let me show you now, and this is another air cleaner number 2, is also photocatalytic air cleaner, and this is just to compare and to show some differences. In the phase 1, we did see, at least in one VOC, for one VOC, we did see emissions directly coming out of the air cleaner. That was the case of toluene. The amount of toluene in the chamber at the end was something like 3 ppbs. It's not a lot. But this air cleaner had, during the initial burnout period, we didn't just take the air cleaner out of the box and install it in the chamber. We had, in each case, we had a fairly long burnout period during which we monitor it and we verify that those initial emissions that sometimes take place were already accounted for, and we didn't want to have our results be confounded by that. So this toluene is what's left after a much larger plume was produced in this particular air cleaner initially. So we see that in some cases there are some emissions of VOCs that are present and that we can measure, and that's easily observable in phase 1, but also in phase 2 we saw the same thing. As you can see, toluene is also higher when the air cleaner is on. Formaldehyde is also higher. This is again a PCO, so the same thing applies as before. So in these other air cleaner, concentrations were actually higher when the air cleaner was running than when the air cleaner was off. Okay, let's see now. Yes?
Ask one question on the baseline. I was a little confused on so the top one was the baseline and the bottom wasn't?
No, the top. Okay, the question is which one is the baseline? No, the top one is phase 1, and the baseline would be the blue bars, which is when the air cleaner is off, and then the red bars are when the air cleaner is on. So
and the bottom one
the bottom one is phase 2, and that is when we first introduce our challenge mixture, and then before turning on the air cleaner, you have the blue bars when the air cleaner is off, and then again the red bars when the air cleaner is on.
It's not net. The bottom one isn't net.
No, no. All right. So next thing we measure is ozone, and in the case of ozone, I would say 4 of the air cleaners did not emit any ozone, but this one, air cleaner number 3, did emit and quite a large amount of ozone, as you see here. As soon as the air cleaner was turned on, the signal went up to really high levels, above 160 ppbs. When we integrated that over the day-long period, it was roughly 160 ppbs, and that was true for both phase 1 and phase 2. So clearly there was, and this is the air cleaner that has the UV lamp that was an ozone-generating UV lamp, so not surprised. The other air cleaner that produced some ozone was the plasma air cleaner number 4. But if you see the plot in the bottom, comparing with the very high levels that were emitted by the air cleaner number 3, number 4 was just a few ppbs of ozone, still measurable, still something we can quantify, but much lower levels. Now, the ozone alone is a problem, but the ozone combined with our challenge mixture of VOCs became an even larger problem because, as we can see here, in phase 1, when we didn't have the challenge mixture, the level of particulate matter was the same. With this gray range there, what we were marking there is the chamber background. The background went up and down, so we kind of mark a very broad background range. But as soon as we introduce our challenge mixture in phase 2, the levels went up quite a bit. And these are ultrafine particles, so this is of concern, is about 6 times higher than the background. And you can also see in the traces that were measured with the condensation particle counter, you can see very clearly the red portions of the curve, which is when the air cleaner was on, how the particles spiked very quickly. And this is due to the very well-known reaction of 2 of our VOCs, styrene and limonene, with ozone. And this is a chemistry that is very well known. I'm not going to describe it in any detail, but just to give you the highlights and particularly the more of the quantitative details here. This is a reaction that is called the Krieger reaction. Ozone attacks the double bonds. Molecules either get fragmented at that position, or if there is a ring, the ring is open. In general, molecules are oxidized by it. So what comes out of it is either smaller volatile compounds that are more oxidized, for example, formaldehyde, that you can imagine very easily formaldehyde being emitted from the double bond in styrene, right? There is this single carbon that will be quickly released as formaldehyde. But the rest of the molecule remains as a larger molecule, more oxidized, less volatile, becomes a nuclei, a nuclei for new particles, and that's the other phenomenon that is well known, which is the nucleation of ultrafine particles. So what I'm showing here is just some numbers. This has been measured a lot, so we have yields of ultrafine particles from both ozone-limonene reaction and ozone-styrene reaction. Remember the numbers 10, 15 for limonene, 3, 12 for styrene. These are numbers we'll encounter again later on. Finally, another thing we did was to measure the ROS with our new method. And in the chamber, when the air cleaners are operating in that big chamber and the air gets diluted with so much other clean air, we couldn't measure anything. That means either the levels of the ROS were emitted were really low, plus our detection limit wasn't low enough. So we couldn't detect anything there. But we did detect at the outlet of one of the air cleaners, the plasma, we could quantify both the hydroxyl radical and the peroxides coming out of that air cleaner. And these numbers, these are expressed in part per trillion. These are really, really low concentrations, but at the same time, these are about 10 times or higher the concentrations that you would normally find in air. So that means there is a level of this species that is much higher than what it should be, and therefore it is a question to ask. I mean, it's a valid question to ask, okay, what would be the effect of releasing these ROS into the air? The main issue we find in this case is that in the presence of ozone, this method had interferences and gave really high signals, but were due to the ozone and not to the other ROS. And this is the main reason why we couldn't measure ROS with the air cleaner that released ozone. Not that it's not produced, but it's just that the method wasn't really able to capture them. So finally, let's go now to some of the modeling, and let me show briefly how we perform the modeling here. The data from these experiments were introduced in a very simple box model in which we had most of the parameters that are shown here, all the airflows, the airflow through the chamber, but also the airflow through the air cleaner, which we could measure experimentally. The source strength, we know how much, what the rate of injection of pollutants, that's something that we know because we inject them ourselves. And the deposition rate, which in the case of ozone, we could measure and also predict based on what is known in the literature. And this is like a summary table for all the measurements. I don't want you to go into the details of all the numbers, but I think it is important to look at the colors here, because the red numbers are those that are emission rates. Those are compounds that are being emitted, that is the concentrations after you turn on the air cleaner are higher than the concentrations before you turn on the air cleaner. And the numbers in black is the opposite. These are removal rates. Concentrations are decreasing with respect to those you had before using the air cleaner. So let's go. The first two lines are important. Ozone is very high. Look at the emission rates are in milligrams per hour, not micrograms, but milligrams. Very high levels for air cleaner number 3, as we saw before. And a little bit lower, I mean, much lower, but still measurable for air cleaner number 4. In the case of particles, we observe the formation of particles in air cleaner number 3. Again, these are secondary emissions. This has to do with the reaction of the ozone with the VOCs that we described before. But interestingly, there are two air cleaners that remove particles. One is air cleaner number 2, which has a HEPA filter. That's not a surprise. And the other one is the plasma, which to me was a surprise. The plasma did remove to some extent particles from the air, and we are going to discuss that more in the next few slides. So let's not look at the details of each VOC, but let's look at the bottom line, the very last row. This is the percent change of the concentration in the chamber. The numbers were either positive or negative, but you see, not that big one way or the other. 14% plus, or minus 12, or minus 8. So within a range of up to 30%, that was a variation that we observed. And that means the effect on VOCs wasn't really that huge one way or the other. And for air cleaners that claim that remove VOCs from the air, that is an important finding, I think. We didn't find a lot of VOC removal overall. Now, how do we process this number? I'm not going to go to show a lot of equations. This is the only slide with equations, but it's important just to follow this more quantitatively. There are two things we could measure. One is the overall efficiency, measured as just the difference between how much was removed over the initial concentration. And the other thing we measure is the capacity, and we call that recycle ratio. Recycle ratio would be the airflow, the ratio between the airflow through the air cleaner or the airflow through the room. Or in other words, the airflow through the air cleaner over the volume of the room at the air exchange rate. And that is a parameter that tells you how many times the air can be processed by the air cleaner before it is removed by the ventilation system. So what we want is for that capacity to be as high as possible, and therefore the overall efficiency to be as high as possible. But the other parameter that we analyzed was what we call intrinsic efficiency. And by intrinsic, in other words, that's how we call the single pass removal efficiency. So when the air goes just one time through the air cleaner, what is that efficiency? What percentage of the VOCs can be removed? And we didn't measure that, but we can calculate that using the equation that is shown at the bottom of this slide, which connects these three parameters. So by knowing the other two, we can estimate what the third was. And I'll give you now, just in bullets, what is it that we found. For VOCs, we could do this analysis for only 4 of the 6 air cleaners, because the other 2 were mostly emitting stuff, not removing stuff. So for the 4 air cleaners that did remove VOCs, the chamber reduction factors were somewhere between 0 and 40%. So the best the one air cleaner did for a couple of VOCs was removing 40% of them, while at the same time the other VOCs were being removed by 30, 20, 10%. So that is one of the most important findings. I think there is a lot of space to improve there in terms of VOC removal efficiency. Related with that is the fact that the recycle ratios are so low. You see 0.4 to 1.7. That means some of these air cleaners didn't have the capacity even to process just once the air that was present in the chamber. So, not surprising that the reduction of the concentrations in the room was so low. Now, when we looked at the single pass efficiency, that spanned pretty much a whole range. Some air cleaners were very effective for some VOCs, but not for others. And I can't go now into all those details, but we do have that analysis done at the compound by compound level. And of course, this 40% limit was only exceeded by limonene and styrene in the case of the ozone generating device. But that's for a different reason, because in that case, ozone was really depleting quantitatively those two compounds in the gas phase. But that was not the process that was happening in the air cleaner. That was just the gas phase ozone chemistry at work. So that's for the VOCs. And in terms of UFPs, the ultrafine particles, as I mentioned, two devices were able to remove some of them. With a HEPA filter, we're not surprised. This was also a device that had the highest recycle ratio, 1.8, still not very high, but you see that with a very effective filter, you don't need to go for the air to be circulated too many times. And you can remove up to 90% of the particles just with a recycle ratio below 2. Now for the plasma had a much lower recycle ratio, but regardless, it removed up to 50% of the particles. And that was surprising. That 50% was even above the theoretical 100% predicted by the model, which assumed that all the elimination was taking place at the air cleaner. And this is comparable in a way with the ozone chemistry for the styrene and limonene. In this case, the fact that the plasma was releasing ions and reactive species into the gas phase, likely, I think this is a hypothesis, facilitated or accelerated the deposition of particles by charging them or by simply changing the chemical surface composition of those particles. And that is something that would be interesting to explore a little further. We couldn't go much further than that in this study. Okay, so finally for the discussion implications, what we did was a couple of very simple models. We assumed in one case one scenario that was a full house, typical sizes, 3 rooms, surface to volume ratios that are what the literature describes for these homes, and also an air exchange rate that is relatively low, but is reasonable, and is what these now newer, tighter homes have in California. And in this model, we use 3 air cleaners, because remember, this is a room size air cleaner, so we had to put 1 per room. The scenario number 2 was a small furnished room, and this was our worst case scenario. What happened if you put the air cleaner in a really small room, you don't use any ventilation, or you have really little air exchange rate, and in this case we had a surface to volume ratio that was slightly higher just because of the dimensions of the room. And here's what we found. In the case of ozone, well, obviously the air cleaner number 3, which was such a high emitter, it exceeded all possible regulatory levels for ozone in that small room. And that is a big problem. Concentration change, delta C, this is what our model predicted would be the concentration change, that is in addition to what was already there, was going up to almost 191 microgram per meter cube. That is, in ppbs, that is, I don't know, 95 ppbs. It's huge. It really exceeds all regulatory levels. Even for scenario number 1, which is a much larger home, the delta C was going up to almost 20 microgram per meter cube, and that is also of concern. This is the kind of ozone levels that you have indoors in Los Angeles, a place where you have very high ozone levels outdoors. For air cleaner number 4, the plasma air cleaner, we could predict an increase of up to 5.5 microgram per meter cube. Again, it's a small increase, but still something that one could measure. In the case of formaldehyde, in again scenario number 2, our worst case scenario, we can see that 3 air cleaners could reach delta C or increase the levels of formaldehyde by around 20 micrograms per meter cube. And this definitely exceeds the California RELs, the reference exposure levels by OIHA, for chronic exposure. So that is also something of concern. The other 3 devices, on the contrary, were removing formaldehyde. Then for benzene, there were 2 devices that produce an excess concentration that was also exceeding California Prop 65 levels for inhalation exposure. On the other hand, there are 4 devices were removing benzene from the air. Finally, we don't have any regulatory level to compare with in the case of UFP and ROS, but still the fact that in one case we did measure UFP formation that was quite significant, and we could predict in that particular case a yield in the order of 1 to 5%, which is consistent with what I showed before was the case for the styrene in particular, but I mean, it was a little lower than the limonene levels, but still in the same range. That is something definitely of concern. And in the case of ROS, yes, we couldn't measure them in the chamber, but the fact that you can measure them at the outlet of the air cleaner means that the ROS are there, and depending on the use of air cleaner, there may be potential exposures happening as well. So finally, just want to summarize this with a couple of conclusions and recommendations. Overall, we see that there are, as I just mentioned, 3 pollutants that are in some conditions exceeding reference levels. Those are ozone, formaldehyde, and benzene. There is this one device that I should mention is not certified. Michael mentioned today at the beginning that ARB has a certification program for air cleaners, and this very high ozone emitter was not a device that was certified by ARB. But there are devices out there that people can buy and can be exposed to really high levels of ozone in the home. And particularly consider this is not a device that is advertised as an ozone generator. The word ozone doesn't come up at all in the marketing material. So clearly there is a need for better standard test procedures. That is something that comes out very clearly from this study, and I had the opportunity to talk with other researchers doing work in this area, and everybody agrees that this is something that needs to be done. We can't really enforce any of this if we don't have any good metrics, and developing those metrics really should be a priority. And then when we look at the specific performance of the devices that we tested, there are a couple of things that conclusions. As I mentioned before, VOC removal is poor, and this is perhaps a good challenge for industry. You know, there is a great opportunity there to improve VOC removal performance, and in general to provide better controls. So if you know that you are emitting a little bit of ozone, for example, in the case of plasma, there may be ways of removing that ozone and making sure that the outcomes that are positive from that air cleaner are not really overshadowed by the fact that, yes, you produce all that great stuff, but at the same time you are producing some ozone that is a negative. So, and finally, clearly the use of ozone generating lamps should be discouraged, and this is relatively easy to do. Okay, so thank you very much, and I'll be happy to answer questions. Questions?
So for VOC removal efficiency, we know those devices you test is pretty low. So do you know if there's any new technology which has higher or potentially higher removal rate for VOC?
Yes, the short answer is any technology has the potential to be very effective in removing VOCs, but the system has to be engineered properly. And my conclusion after seeing at least a few devices that we tested is that in general, if you look at the amount of catalyst that goes in it, the positioning of the lamps, and in general the design of the devices is something that clearly doesn't have enough capacity to process the amount of VOCs that we are talking about. Of course, there are other technologies that we didn't mention here that have been used for a long time. Adsorption is good at capturing a good amount of VOCs. There is also chemisorption, which is a very mature technology. Both of those are really effective at removing VOCs. But in all cases, you know, the engineering and dimensioning of a system should be right. And that's particularly in the case of portable air cleaners. I suppose there is a cost issue associated with it. And also you want to minimize the size and the volume of the device. And in the balance, I think that the performance really is one factor that is lost.
We have some internet questions that we will address now. One question came in. Manufacturers claim these technologies reduce microorganisms. Any plans to test effectiveness of these claims in addition to VOC claims currently tested for?
Well, definitely, that is a very important question, and our lab, at least at the moment, we are not set up to do that, but I'm pretty sure that this is something that has to be done. Similarly to this, I mean, a good test protocol should include both VOCs and microorganisms. And there are many different microorganisms, so it's not just one test, there may be several tests that are needed.
Then we have a multi-part question, so we'll go through it one question at a time. First of all, 6 air cleaner models were tested. I know that you don't want to endorse, vilify any specific models. However, will you disclose which models were included in the mix? I'm not asking to name or associate any specific models with any specific data set, so are we going to disclose the models?
Well, I mean, for the purpose of this study, we felt that it wasn't really necessary. We tried to select devices that were fairly representative of what's out there. So we didn't pick one particular, weird case. So I think the conclusions can be generalized, and I don't find that it's really necessary to provide that information, and at the same time, it would be unfair to do that. So.
Okay, and then can you please explain why ultrafine particles need to be measured, and are they dangerous?
Okay, well, that's easy. Now, clearly, the ultrafine particles are smaller than 100 nanometers, and those are particles that can reach into the lung, deeper into the lung, and therefore are associated with health, problems, and therefore we can measure them now better. And in part, one of the reasons why, we only regulate for what is called PM2.5 and PM10. This is a range of particles that, although includes ultrafines, goes beyond that. It's all the particles that are smaller than 2.5 microns and 10 microns, respectively. And as now the technology becomes more standard and more widespread, and we can measure ultrafine particles on a regular basis, there may be, and I'm not familiar with them, so I'm sure there may be I'm not perhaps the best person to answer this, but I would say that there may be good reasons for regulating ultrafine particles as well.
And then finally, does ozone have any good uses for air treatment?
I don't think so. The problem with ozone itself is that, clearly ozone is a great oxidant. It is used to treat water. So you would say, okay, why not to treat air? The problem is that it's very difficult to use it and then to remove it completely so that it doesn't filtrate into your room. Suppose if you had an air cleaner that had ozone inside, and you could benefit from all that oxidative potential of ozone, but then ozone could be removed completely and not vented indoors, then I would say perhaps. But it's very difficult to do that. Especially if you use very high levels, then not. Ozone is used for things like restoration when you have a flood, or sometimes people want to treat an environment that has been impacted by tobacco smoke or other odors. And in that case, yes. If you don't have people in the space when you blast the space with ozone, clearly it has a benefit, and you can remove stuff, or at least potentially it has a benefit. You have to look in more detail, but that is something that is done, and it has some potential benefits. But then, of course, it has to be an unoccupied space. And then you have to allow for enough ventilation, not just for the ozone to be removed, but also for some of the oxidation products produced in that process to be removed as well.
Okay, another question regarding slides 19 and 20. Could you comment on how you arrived at these challenge levels of substances?
Okay, well, we looked at the literature. There are a number of studies in which people went into homes and measured what the concentration of indoor pollutants was. And we took 3 of those studies. One was carried out by ARB in particular. So and also we try to look for things that are recent and particular studies that were carried out in California, because there are maybe some local effects or some materials that are used in some areas that are not in others. So we mostly look at the list of, it was a very long list. It was a page-long, table of compounds, and we selected from that table the compounds that were most predominant and that we know that are present, and that and also at the levels that they were present there.
Any other questions from inside?
Thanks. Hi, this is Kevin Messner. I represent the Association of Home Appliance Manufacturers. Just one very specific question. On the placement of the air cleaner in the chamber, where did you put it? And did you put it the same place every time, I assume?
Okay, good question. I forgot to mention. It was always in the center, and we had 2 fans to ensure that the air inside the chamber was well mixed. Thanks for the question. Yeah.
Thanks.
Yes, Peggy Jenkins. Thank you, Hugo. Just overall, from your results, do you have a sense, were the majority of the VOCs that were produced from secondary reactions, or do you think it's primary emissions, or do you have a sense, is it 50-50? I don't know.
I would say it's mostly primary emissions.
Oh, really?
And
Okay.
the 2 air cleaners that were the higher emitters are those that are mostly have a plastic casing, and they're mostly built on plastic. The other ones, for example, the air cleaner number 1, which was really not emitting almost anything, was mostly metal. And this is not different from what we observed with office equipment. Very similar. These are, several kilograms of plastic that are heated inside. Not surprisingly, there are VOCs that are coming off. That is...
Right.
Yeah.
Okay, thank you. Any others? Mike, you wanna do next?
A few more internet questions. Here's another one. Are charcoal/HEPA air filters being considered? I assume the charcoal would increase the VOC removal.
Definitely, yes. And in general, for these room size air cleaners, there is an issue that has to do with the size and the weight. The shape of these devices are, half of them were those tower-like, that are about a meter or so tall, and the other ones were more like boxes that could be either tabletop or relatively small. So the amount of charcoal that one had to put inside any of these devices for it to be effective would be, would require a much larger device. It's not impossible. It's just that it becomes a different type of air cleaner, and we didn't go into those air cleaners. Air cleaners that are more for specialty applications, whether it's for hospitals or classrooms or industrial applications. That's a different story. There is a lot more particular activated carbon used is used a lot more in those cases, but clearly not in the type of devices that we were looking at here.
Another internet question. Can you clarify that if the exchange rate were to increase with these products, would the VOC reduction rate also increase, perhaps higher than 40%?
Okay. I cannot guarantee that. What is true is that with such a low capacity to process the room air, regardless of which technology you use, you would only be able to process the air that goes through the air cleaner. So clearly, on one side, I feel inclined to say, yes, you need more capacity. That means you need to process more times the air. That is a larger fan, things like that. At the same time, there is another issue, which I didn't mention, which is photocatalysis is a multi-step reaction, so you need to keep the compounds or the VOCs in contact with the catalyst for some residence time that is short, but still has to be a few hundreds or tens or hundreds of milliseconds. So if you start to run air at a much higher flow, the residence time will be lower. So from that point of view, you have a trade-off between increasing the airflow and increasing the capacity, but at the same time reducing the residence time each time the air cleaner goes through. And in some of the work we did in the past, that's exactly what we observed, that if you reduce that residence time too much, you start losing capacity or losing the performance again.
Any other questions from the audience? Another internet question.
Okay.
I have schools asking about using ozone for controlling skin infections and odors in locker rooms. I'm looking for research on the efficacy, and is it even worth it with the need for thorough ventilation and flush out afterwards?
So if I understand well the question, this would be releasing ozone when the kids are not there, right? I mean, if it's to control for skin infections and odors, that has to be, yeah, probably. Well, clearly, if that's done, you need to control to be sure that ozone and its byproducts are gone by the time the space is occupied again. And that's not easy to do. So, I mean, ozone is relatively easy to do, the byproducts are not. And sometimes the byproducts themselves can be odorous. So you can have a residual odor that has to do with the fact that you had used ozone before. So it's, I mean, that goes into another area. This is not what we studied here. I just want to clarify that this goes into more of the restoration or the use of ozone as a with that other type of purpose. And that, I should say, that requires also a lot of more research. And I see that this is a very active field. There are a lot of companies out there that offer that service. And I haven't seen a lot of studies showing this type of, both the benefits and the potential risks. So that is something that is really is interesting, and it would require more work. I think it's, but we'll leave it there.
One other question, which I realized we never really, asked you. So you had to select, 6 types of units. I recall in the beginning of the study, we went through a whole list of different technologies and narrowed it down. But now with the results you've seen, what would you consider important follow-on steps? I mean, one question that came up is effectiveness with microorganisms, and that's one we all know we have to deal with. But what follow-on research do you think would be important along this line in terms of, not just VOCs, but efficacy of air cleaners?
Well, there are a number of interesting questions that came out, and like you mentioned, with only 6 air cleaners, one can only start scratching the surface here. One is both in terms of increasing the capacity and increasing the controls. What are the key aspects of an air cleaner that could be tuned or modified to do that? And this is something that, in principle, you would think that industry should be interested in doing that themselves, and at the same time, it's something that is needed. The other one is the test methods. We don't have a test method, and having any type of standard methodology that can be applied and is acceptable by all parties could be a really important benefit. Because one thing we found here is that the market is large and is growing, and really it's a market without any rules. People can go and sell anything, claim all kind of benefits, and really there is no way to prove whether that is true or not. Even if they wanted, even if a company wanted to prove that what they are doing is much better than their competitors, there is no metric, no yardstick to use. So I would say that to me is the number one priority right now, apart from the microbial. Yeah.
All righty, if there are no more questions from the audience, we thank you for joining us, and thank you to all of the folks that joined us via the web. And thank you, Hugo, for a wonderful project.
Thank you.
And have a good afternoon. Bye-bye.